Hello and welcome to lecture 62 of the course Computational Complexity. So we saw interactive proofs so we first initially defined the class IP, which just said that there should be communication, there should be interaction between the prover and verifier. Then we saw the classes Arthur-Merlin classes, where we said that the verifier has to compulsorily send the random bits across to the prover. And so having to compulsorily send the random bits to the prover is kind of a restriction, because we saw that in the case of graph non-isomorphism proof, we could benefit by hiding the random coin from the prover. So the question is, so this restriction, how does it make things, how restrictive is this restriction? Right? Is there something that we cannot do with insisting on public coins that we could have done with private coins? Right? Was there some language that we could decide using an interactive proof system with private coins, but cannot decide with the public coins system? Right? So that's one question. Right? For instance, can you decide graph non-isomorphism in a public coin setting? How many rounds does it take? What resources does it take? Right? So this is a question. So this was answered by Goldwasser and Sipser, who said that for any k, right, any k need not be a constant. If something can be accomplished by an interactive proof in k rounds, right, then the same thing can be accomplished by a public coin interactive proof in k plus 2 rounds. So basically, 2 additional rounds are enough to convert a private coin protocol to a public coin protocol. So at first this seems kind of impossible, because in graph non-isomorphism, the keeping the random coins private was essential. Now how is it possible to convert it into a public coin protocol where the verifier has to send across the randomness, right? Well, we already saw some example in the sharp 3 set instance, right, where we could use randomness in a clever way. So the key thing there was that the verifier will generate random coins only when required, and the prover was forced to commit certain things before knowing the randomness. And because he didn't know what randomness is going to be generated later, right, because, well, they're random, that helped the verifier, right? That helped the prover, or that helped the system to be more robust, right? So that prevented the prover from cheating, right? Because he does not know what randomness is going to show. Nor does the verifier know, but verifier does not care. Verifier just is waiting for the prover to convince him, right? So so the idea is that we will send information only when, or we will send the randomness or generate the randomness only when necessary. Okay, so this was Goldwasser and Sipser's result. So instead of showing this result in the full general setting, we will just show that graph non-isomorphism has a public coin protocol with just 2 rounds. So in fact, graph non-isomorphism has a Arthur-Merlin protocol with 2 rounds. So we had already seen that graph non-isomorphism has an IP2. Now we say that it is an AM2 as well, right? And the ideas are very similar. So it is probably more instructive or simpler to see for a specific problem, for a specific case, rather than the general situation, right? So the proof will be easy to follow once you understand this. Okay, so the result that we will see, again using this is also Goldwasser-Sipser's, is the graph non-isomorphism has an AM protocol, AM proof system with 2 rounds. Okay, so let us recall what was graph non-isomorphism. It consists of 2 graphs such that they are not isomorphic, G0 and G1, and we saw graph non-isomorphism in the previous lectures. And so what was the earlier protocol? The earlier protocol was that verifier picks B from 0, 1 right, and a random permutation, so sigma, and then sends H, which was sigma of GB. So if B was 0, he would send a permutation of G0. If B was 1, then he would send a permutation of G1. And the prover had to decide where this graph H came from. Did H come from G0 or G1? Right? If G0 and G1 are isomorphic, then H could have well come from either one. There is no way the prover could tell. If the graphs are not isomorphic, then the prover, using his infinite power, should be able to compute and figure out where it came from. Right? So, and that was the principle that we used for the private coin protocol, private coin proof system for graph non-isomorphism. Right? So the message that the verifier sends is the graph H. So what are the possible graphs that the verifier could have sent? Right? Let S be the set of possible graphs that the verifier could have sent. Now, if G0 is equal to G1, right, which means it's a no instance for G0 is isomorphic to G1, which means it is the graphs are isomorphic. So it's a no instance for the graph non-isomorphism problem, because it's a graph non-isomorphism is a language, right? So it's a no instance for the graph non-isomorphism problem. In that case, G0 and G1 are the same graph. So the set of graphs that could be sent by the verifier is just the permutations of that one graph. There are n factorial ways to permute a graph or permute the vertices. Right? Permutation is just a reordering or relabeling of the vertices. So there are n factorial different graphs that the verifier could send. Well, there is a small detail here on something called automorphisms. So we are currently ignoring it. So automorphisms are basically some relabeling that, what if multiple relabelings look the same, right? So for instance, some simple graphs, if you relabel it in two ways, it still look the same. So it will actually bring down the size of S to something below n factorial. But I do not want to get into that, mainly because that particular detail is not really that crucial for this proof. So I'll tell you why it is not crucial. If G0 is not isomorphic to G1, which means G0 and G1 are not isomorphic, right, which is a yes instance for graph non-isomorphism, then the set of graphs that can be sent by the verifier, there could be n factorial permutations of G0 and n factorial permutations of G1. So there will be 2 times n factorial graphs that the verifier could possibly send. Right. Again, there could be automorphisms, but that will again bring it down from 2 times n factorial to a smaller number. But the key thing is that what we will exploit in this is the size of S, which is a set of possible graphs that the verifier will send. The size of S, how different is it in the yes case and the no case, right? So we want a sizable gap between these two, between the number of graphs that could be sent in the yes case and the number of graphs that could be sent in the no case. So the exact number n factorial is not that crucial. What we are interested in is in the gap, and even the automorphism can be fixed by doing some things. So you can look at Aurora Barak, where they do something to fix this automorphism issue, but I do not want to get into that detail because it's not very instructive on how to fix that. You can read it if you are interested. I want to just touch on the core idea that is used by Goldwasser and Sipser, and what they use is the way to tell the differences of the sizes in the yes instance and the no instance. And just to amplify, so now as it is, there is between the yes and no instance there is a factor of 2 difference, right? 2n factorial and n factorial. Just to amplify it a bit further, let us consider the set S prime. Okay, S prime is just a Cartesian product of S. So think of it as instead of Cartesian product, you can think of the verifier generating 4 random bits and 4 permutations and sending 4 graphs. So H1, which is a permutation of one of them H2, which is a permutation of another one, H3, which is a permutation of another one, and so on, right? So what is the total size of the set that verifier could have sent it from? If it's a yes instance, so now you can think of it as the whole the set of things that is sent by the verifier is from S cross S cross S cross S. So it is n factorial power 4 if it's a no instance, right, because both the graphs are the same, and 2 times n factorial power 4, which is 16 times n factorial power 4, right. So when it's a yes instance, right? So this is a no instance and this is a yes instance. So basically it's just the fourth power of the previous answers. So here the thing is that because by taking the fourth power we have amplified the gap, right. So here we have amplified the gap from 2 to 16. This is a bit convenient. Even with 2 I think you can reason a proof, but then a bigger gap makes for an easier explanation. So, and the protocol that we will see is called Goldwasser-Sipser set lower bound protocol. That helps us distinguish between these two sizes, n factorial power 4 and 16 times n factorial power 4. So n factorial power 4 is not very important. What is important is the 16 factor gap. Okay. So all that we will need is the 16 factor gap. So it's like this. There are two possibilities that the verifier is in, or there are two possibilities that they are in. Either the graphs are isomorphic or they are not isomorphic, right? So in one case, the number of messages that can be sent by the verifier is k. In the other case, the number of messages that can be sent is 16 times k, or maybe in other words, it's like in one situation the number of messages is k, and the other situation it is k divided by 16, right? The 16 factor gap, and the protocol will try to tell if there is a difference between these numbers. It will tell whether you are in the k case or k divided by 16 case, right? So let us see, and the next property that we will use is that we'll come to that. I'll explain when we come to that. Right. So choose a hash function h that maps S to the set 1, 2, 3 up to k divided by 4. So notice that k divided by 4 has a 4 factor away from k and 4 factor away from k divided by 16. So it's somewhere in the middle. Okay. And this is chosen from a pairwise independent hash family. So this we had seen in lecture 48 where we explained Bailey and Vazirani lemma. So pairwise independent hash family is basically a family of functions that behave in a random like manner. In the formal definition, you can go back and refer to lecture 48. So if there are two hash functions, they will act as if they are independent with each other, right? So the probability that h of x maps to, let's say, 1 will be h of x could be either one of 1, 2, 3 up to k by 4 all with equal likelihood, 1 divided by 1 by k, 1 divided by k by 4. Okay, so it behaves in a random like fashion. That's all that we require for this proof. Okay. So if we choose the verifier chooses a hash function from this pairwise independent hash family, okay, and then it chooses a y from the set 1, 2, 3 up to k by 4. So basically from the range of the hash function, and the verifier sends h and y to the prover. So notice that the verifier only chooses the hash function and the number y, both of which the random choices are just being sent to the prover. Okay, so it's sending the entire randomness. Right? Again, this is what we want in a public coin protocol. And what does the prover do? The prover finds, and the prover's task, the prover is all powerful. The prover has to find some element x in S such that x maps to y. Okay, so it's like this. right? So this is the set 1, 2, 3 up to k by 4. Right, and this is the set S. Now, given a certain y, the prover has to find out, is there an x that maps to that y, and if there is an x that maps to the y, the prover will send that value x to the verifier. So notice that the verifier cannot identify such an x, because s itself is like n factorial or some big number, right? So it does not have the time to go through all the elements of s, right? So, but prover can find and send the x, and notice that x is in S means x is possibly an element that could have been sent by the x is possibly an element that could have been sent by the verifier, and the prover can say that, well, this is an element that you could have sent, because you take G0 and you permute it, you get x, or you take G1 and you permute it and you get x. This is something that the prover can tell the verifier, right? So it can tell the proof that or the certificate that x is in S, right? Because S itself is too big to list down, but to convince the verifier that x is in S, it can tell that so this is just an example certificate will be like take G0 and permute with, let's say, sigma 1 to get x, something like that. And this the verifier can verify, so that the prover does not cheat him, saying that this is something. So now, given x, the verifier can verify that x is indeed an element of S, and second, the verifier can also verify that x maps to y, right? Because the hash function is easy to compute. So once this is done, once the verifier verifies this, that x is in S and hx is equal to y, it accepts, verifier accepts. If he cannot verify this, he will reject. So the prover cannot lie, because the verifier is verifying everything. So the only thing, the prover will be successful if he can find a y, he can find an x in S that is a pre-image of y, right? So prover's goal is to find an x that is a pre-image of y in S. So this is the goal. And when will the prover be able to do that? And all the probability, completeness and soundness boils down to this: how likely is the prover able to find a pre-image of y in S? That's it. So this is S, this is the set 1, 2, 3 up to k by 4. Right now, how likely is the prover able to find a pre-image of y? So let's say the completeness. Completeness means it's a yes instance, which means the graphs are non-isomorphic, in which case the set S is large. Okay. So completeness means it's non-isomorphic, so it's S is of size at least k. Then what is the probability that the verifier will be convinced? If S is of size k, right, then the point is that most y will have a pre-image in S, because S is of size k. So you map each element of S into, let me call this set T. Okay, so T is equal to 1, 2, 3 up to k by 4. So when S is as big as k, then most elements in T will be mapped by some element in S, simply because S is 4 times bigger than T. So that is the intuition. So consider So to see the probability, consider S hat, which is a subset of S. So suppose S is at least K, right? So consider S hat as a subset of S, where S hat is of size exactly K. Okay. Consider S hat and of size exactly K. Now what is the probability that no element from S hat maps to Y? Okay. So S hat is of size exactly K, and here we have T and there is a certain Y. So what is the probability that an arbitrary element misses Y? Right. What is the probability that an arbitrary element misses Y? The probability that an arbitrary, it's a pairwise independent hash family. So an arbitrary element misses Y, let's say with probability. So one element misses Y. So probability that let's say Z, h of Z for a specific element Z is not equal to Y. It is equal to, so the probability that h of Z equal to Y is 1 divided by K by 4. So this is 1 minus 1 divided by K by 4, right? So in other words, it's 1 minus 4 by K, that Z does not get mapped to Y. What is the probability that none of the elements in S hat maps to Y? It is 1 minus 4 by K whole power K, because there are K elements in S hat. And this is easily upper bounded by e power minus 4, right? This is easily upper bounded by e power minus 4. So this is the probability that no element in S hat maps to Y. Okay. So what is the probability that Y has a pre-image? That is the complement event. Some element maps to Y. So what is the probability that Y has a pre-image? It is at least 1 minus e power minus 4, which is way bigger than 2/3. This is 1 minus e power minus 4 is much closer to 1, right? So probability that Y has a pre-image in S hat is at least 2/3 in the S instance. And in the no instance, we want to show that the probability that Y has a pre-image is at most 1/4. So that is a soundness. Suppose the size of S is at most K by 16, right? This is S and this is T. So let me just write T as bigger, or draw T as bigger. Then S has at most K by 16 elements and T has K by 4 elements, right? So size of T is K by 4, size of S is K by 16, right? So which means even if each element of S maps to a distinct element in T, even if that happens, at most 1/4 of the elements of T are covered as images of elements of S, right? So at most 1/4 of the elements have images in S. So which means at least 3/4 of the element in S do not have pre-image in S. So the probability that Y has a pre-image in S is less than 1/4. So it has to be, so the size, the number of elements in T that have pre-image in S will be at most 1/4 T. It cannot be bigger than this. So the probability that Y has a pre-image in S is at most 1/4. So it's 1/4, which is less than 1/3. So the completeness and soundness have been checked. Okay, just one more point in the completeness. We said that the probability Y has a pre-image in S hat to be at least 2/3. We said that S is a superset of S hat. So the probability that Y has a pre-image in S will be at least this. So maybe I'll just write that here. Probability that Y has a pre-image in S is less than or equal to this. So we have completed the completeness and soundness, and using this protocol, the prover and verifier can be convinced, or the verifier can be convinced by the prover that either the graphs are not isomorphic or they are isomorphic, right? Or they're not non-isomorphic. So notice that once again it is a public coin protocol because the verifier sends H and Y, which were the random choices, and the probabilities check out. And it's a 2-round protocol. The verifier sends H and Y, prover sends a certificate, and then the verifier does not do any other random generation or anything. He just performs the verification, and that's it. So this completes the proof that graph non-isomorphism has a 2-round Arthur-Merlin proof. Arthur-Merlin in the sense public coin interactive proof for graph non-isomorphism. And the proof that for the general Goldwasser-Sipser theorem is also very similar, but I am not getting into that. So there we require 2 additional rounds. Okay. But when k is constant, am k plus 2 also is a constant. So we have already seen that am k plus 2 is equal to am when k is a constant, because k plus 2 is also a constant. When in other words, another point is that when k is polynomial, when you have polynomially many rounds, IP and AM are the same, right? Because you just have 2 more rounds, it's still polynomial. So when you have polynomially many rounds, public coin, private coin doesn't really make a difference because we are both polynomial. Anyway, so we've seen the proof that the Goldwasser-Sipser proof that you can convert private coin protocols into public coin protocols. The key idea that we used was the difference in the sizes of the sets. Okay, and that completes the main theorem, and that completes most of almost all of what I had to say on interactive proofs. So let me just summarize what we have seen so far. We saw interactive proofs which generalize this NP and BPP, where you could have a interaction with the prover, right? Not just operate on a static proof given to you, right? And how powerful is this? So we first saw that when the verifier is deterministic, it is only as powerful as NP. So then we moved to a randomized verifier. Then we saw properties, and then we saw this graph non-isomorphism proof with which is a problem in co-NP using a private coin setting. Then we saw properties like completeness, soundness, and so on. We said that IP is contained in P space, and we saw the proof that sharp 3 set is contained in IP, so which is actually a sharp P complete problem. So the power of interaction is way more than NP or co-NP or sigma 2 or something. The sharp 3 set is much above that. Right? We saw that sharp 3 set has a public coin interactive proof system, which use public coins to a very telling, very nicely using public coins. The proof system could convince the verifier that the number of satisfying assignments to a Boolean formula is equal to something, which was a sum check protocol. And I also mentioned the fact that IP is equal to P space. So the P space complete language TQBF can also be shown to have a interactive proof system. So in fact, that the same proof system that we use for sharp 3 set can be modified to get an interactive proof system for TQBF. So basically we have to add deal with how the existential and universal quantifiers are going to be converted into arithmetized, right, into the arithmetic setting, and some additional ingredients are required, which I didn't get into. I strongly recommend reading this article, which is a somewhat of an informal article, and it just gives you a nice overview of the way the area had developed in the 80s and maybe early 90s. After that, we saw public coin proof systems, AM and MA. Right? We saw that AM and MA are the only 2 public coins proof systems, and we saw that AMK reduces to AM, which is AM with two rounds. We saw that MA is contained in AM. We saw that graph isomorphism is unlikely to be NP complete, because graph isomorphism, if it is NP complete, then sigma 2 equal to n pi 2, and the whole polynomial hierarchy collapses to sigma 2. One point that I missed to note when I stated this is that this is a nice theorem that graph isomorphism is unlikely to be NP complete, right? But then if you look at this theorem closely, you see that this statement of this theorem, right, just the statement, graph isomorphism is NP complete, then sigma 2 is equal to pi 2. This has nothing to do with interactive proofs. I could have stated this theorem at the time when we saw polynomial hierarchy, and you would have understood this theorem, right? We don't need to know interactive proofs to understand the statement of this theorem. But this proof or this statement has a proof using interactive proofs, and as far as I know, whatever proofs are like, there are small like the proofs that are there for this statement are all using interactive proofs, right? Maybe slight variations of one another if you look at one reference from the other, but then the statement itself is completely a statement only on sigma 2 pi 2 and graph isomorphism, right? It has nothing to do with interactive proofs. So it is very interesting to see that interactive proof systems, the technology of interactive proof systems, is able to show statements like this which are completely free of interactive proofs, right? So this is something that is very interesting, and you could say that this is one reason why it was worth pursuing the interactive proofs, right? And we saw that graph isomorphism is unlikely to be NP complete, and then we saw that you can simulate public coin proof systems, private coin proof systems with public coins. Right? We saw, we didn't see the entire Goldwasser-Sipser theorem, but we saw that graph non-isomorphism as a public coin proof system. So what we had seen was a private coin proof system. So this is the set lower bound protocol by Goldwasser and Sipser, which used the fact that in the yes instance and no instance, the size of the range of messages that could be sent by the verifier could be vastly different, and this is exploited in this proof system. Okay. And one final point that I wanted to make is that there is something called probabilistically checkable proofs, which is an area that got created from the interactive proof systems, right? That was an offshoot of interactive proof systems, where you can, so it is like an interactive proof system where you can convince, where the prover and verifier the prover convinces the verifier of some fact, and the verifier does not have to look at the entire proof. The verifier just looks at some sub part of the proof. And this was also a success of the interactive proof systems. And the theory of PCPs, or the probabilistically checkable proofs, later was pursued in the 90s and early 2000s to prove a lot of results in the area of the hardness of approximation. So I'll not get into what the hardness of approximation is, because then it gets to too much. So the inability to approximate certain languages or functions, right? And so this is this was an offshoot of the interactive proof systems. And if you read the brief history of PCPs by Reinhard O'Donnell that I mentioned in the previous part, right? One of the previous parts, you will see this as well. It's actually for this is the PCP that he refers to there. The history of the PCP theorem. And with that, we conclude this week's content on interactive proofs. And this being week 12, I would also like to summarize the entire what we have seen over the entire 12 weeks, which I will do in the concluding video, in the concluding lecture, next lecture. Thank you.